Now we will do a PCA, Principal Components Analysis. Okay. All right, and this is the big idea here is kind of it's useful for dimension reduction. And identifying structure in the data. That light is flickering. And so this, again, falls under kind of the umbrella of unsupervised learning. Okay, so it's another. Okay. All right. So here's a kind of a, I don't know. So, imagine you've got like a house prices data set. Okay, and it might have like many variables. It could be like square footage, number of bedrooms, number of bathrooms, lot size. It could be like kitchen quality, like type of floors. I don't know, lots of stuff, right? The roof quality, things like this, age of house, or when built, when last remodeled. There could be stuff like crime rate of the neighborhood. Yeah, school rating. Maybe median price of the 5 nearest homes. Things like this, okay? Et cetera, right? You can have like 80 variables on a house, okay? All right, you want to do some analysis. You want to say like what's related to predicting the price, right? And I guess the other parts will just be like the name of the neighborhood, right? Which neighborhood you're in, et cetera, et cetera. Okay, what's related to price? And so probably everything is related, sort of, but can we reduce the number of dimensions? And we're going to find that a lot of these things are related, right? Like all of these things, they're probably going to be related. You got more square footage, you're going to have more bedrooms, you're going to have more bathrooms, you're going to have, they have like living space and basement area and whatever. They have all sorts of stuff, right? And we might be able to just say, we can kind of turn all of these, there might be like 80 plus variables or something, okay? And we might be able to reduce them into just like 3 variables. Basically, size, quality and amenities, and neighborhood quality. Okay, and so you can just, the size can be something like it's a big house versus it's a little house, okay? Without needing to get into the details. You say big house, that's going to mean it has a lot of area, more bedrooms, more bathrooms, and exactly how many bedrooms, how many bathrooms is less important. It's just the idea of big versus little, okay? Qualities and amenities could be things like, basically on the fixer upper spectrum side of the spectrum versus like ready to move in and nicely furnished, nice floors, nice kitchen, nice roof, nice windows, nice whatever, right? All sorts of things, recently remodeled versus like stuff is falling apart and is in need of serious repair, okay? And then neighborhood quality, is this an expensive neighborhood? Are all of your neighbors rich and like the schools are nice? What? Yeah, and versus you're kind of in a less desirable neighborhood, right? And maybe a lot of these things can be kind of boiled down to just these three, and we can do this because maybe you're familiar with housing and stuff, and you're an expert. But can we do something similar to this? I guess mathematically, okay. And so we get to this idea of reducing the number of dimensions via PCA. So that's kind of an idea. And so what PCA will do is it will project what we're going to call this a projection, project higher dimensional data okay, quote, project down to, quote, fewer dimensions. Right, so it projects higher dimensional data down to fewer dimensions. All right, so what do I mean by this, okay? I mean, so my hand is a three-dimensional object, okay? And I'm gonna hold it in front of the light and it will cast a shadow, okay? So what you see in the shadow is a two-dimensional projection of my three-dimensional hand, right? And I have a few ways of holding it, right? So if I do this, you can see the shadow and it looks like a hand, right? But if I do this, it's not as clear what this might be, right? And so we don't want this, right? This doesn't show clearly what the shape is versus this makes it more clear that it's a hand, right? And so just like anything else, any object you have, like here's a pen, and if I hold it like this, then it's very clear what kind of that it's a pen. Whereas if I held it kind of like this, then it's just this tiny little dot, okay? And that would be a poor projection, okay? So what we want to do is we want to find a projection of the data so that we kind of maximize the technically we're going to try to maximize the variation in the projected data. All right, so we want to find a projection that will maximize the variation in the resulting projection. Okay, so for example, the original data, maybe it exists in 2 dimensions. Okay, maybe it looks like this, okay? And I want to project this, let's say I want to project my 2-dimensional data down to 1 dimension. Okay, so I have a few choices here, okay? Let's see. So one, whoops, that's not what I want to do. One is I could see, here's my source of light, okay, and the projection, the shadow will be right here. Okay, the shadow of these points will end up like each of these dots cast a shadow down to here. Okay, and so now we have one-dimensional data. Okay, so the light each dot casts a shadow right there. Okay, a poor choice. All right, so I guess this is okay. All right, not so great would be if I choose to put my projection here, and so my light is shining this way, right? And then everything, if I do this, then kind of the perpendicular line would be here, and everything, all of these dots would just kind of end up like right on top of each other, okay? And so we lose a lot of, like, we don't get a sense of the different data points, okay? And so this is not good. Okay, and then, and kind of, I don't know, the best would be something coming this way so that the resulting projection comes over here, and the shadows all end up right here, here, here. You know, I get 2 points on top of each other here, there, there, and there. Okay, and so this kind of maximizes the resulting variation. Okay, so this will be kind of our choice PCA projection. You know, if there were kind of clusters in the data, you know, trying to maximize your variation. So if you had some data here and some data like this, okay? So a poor projection, like if you projected it all this way, all right? So if your source of light comes this way, then the resulting projection, you wouldn't be able to tell, you know, everything just ends up kind of right along here, okay? It's hard to distinguish points from each other, okay? Whereas if you projected it from here and the light's coming this way, then you would get you know, you'd get some dots over here, and then you'd get dots over here, okay? And then this would kind of preserve the fact that clusters exist, right? So this there's more variation here, and it kind of preserves the clustered nature of the data. All right, so what is a projection, okay? Well, a projection is going to be a linear combination of the different variables, okay? So the we'll say the original data exists in m dimensions, okay? And what we want to do is we want to project the data down to d dimensions, okay, where d is less than m, Okay, so d is a smaller number than n, and we want to project d, okay? All right, so PCA will define d vectors, okay? Each of these vectors will be a, quote, like a recipe of how to combine the m original dimensions. Okay, so we will get like, so each vector we're going to call will be w sub d, okay? Each vector w sub d is m dimensional. And what it's going to have is the values in WD will be like the weights of each of the m original dimensions. So you might have, if you started off with 3 dimensions and you wanted to project down to 2, okay, then you would have 2 of these weight vectors, and it would say use like, I don't know, 100% of x, 30% of y, and 70% of z, or something. Some weight on each of these things. Okay, so each vector WD is m dimensional, and the values in this vector WD is the weights we use for each of the m components. I guess m variables, okay? Okay, so we can say our original data would be matrix Y, and this is n by m dimensions, okay? And then we're going to have a matrix W, which is m by d, okay? This is basically consists of kind of basically all of these WDs together. And when you multiply that together, you get x, which is going to be n by d. Okay, so each observation in x, or each row in x is xn, and is a d-dimensional vector. Okay, and okay, and then okay, so if I take one of these things, so like the first weight thing, and I kind of transpose versus one of the observations y sub n, this will be x and d, okay? X and d is the dth value in the basically x of n observation. Okay, I guess converted observation, or I would say projected observation. So you've projected down to d dimensions, and x and d is that dth observation here. okay? So if we started off in a 3-dimensional object, okay, and we projected down to 2 dimensions, then this might be like the, your first observation. You could be like the second dimension of the first observation, or the first dimension of the first observation, or something like that. All right, and what we want to do is we want to what we want is the values in x of nd to be kind of maximized. I'm sorry, the variance of in our projected values of x to be maximized. Okay, so we want to maximize the variation in our projected data x. Okay, and because that's what principal components analysis will do. It's going to find the projection, it's going to find the w's, so that the resulting product, when you take w times y, will result in the x with the maximum variation. Okay, so we want to maximize the variation here in our projected data x. Okay, so kind of to simplify the math, and I hesitate if I really want to do all of the math, but okay, but I'll just run through it. Okay, to simplify the math, we will start with a centered data matrix y. Okay, so we're going to start with the centered data matrix y, so that if I take the mean of each y, we're going to get 0 for basically all of the columns. Okay, so the data in y has been centered, so basically each column has a mean of 0. Okay, so each column in y has mean equal to 0. All right, and that just makes our math a lot easier. Okay. All right, and so I'll just say let's project y down to 1 dimension. Okay, and so basically x of n is going to be a single scalar value to represent observation n. Okay. Well, before I get into this, let's just pause for a second. Okay. So, so like the simplest idea, not the simplest, but like one very simple idea of dimension reduction is let's just add the values in x together, right? So you take your SAT exam or whatever. I don't know if you ever took the SAT, but okay, when you took the SAT, there was like a math part and a reading part. Maybe there was even a writing part. Okay, but okay, so there's a math and a verbal, right? And you get like score between, I don't know, something up to 800 for math and something up to 800 for, I think it's between 200 and 800, right? Those are the min and max, okay? Between 200 and 800 for math and 200, 800 for verbal, right? Okay, all right. Dimension reduction, you can go from 2 down to 1 just by adding them together, right? And then so if your combined score is 1600, that you did perfect. And you can just take your SAT combined and say, whatever, we scored 1300 or 1500 or whatever, right? And And that's fine, right? That's dimension reduction, okay? And that would have a weight of basically 1 on the math part and 1 on the verbal part, okay? And you would just do a 1, 1, and you multiply the weights by the raw scores, and you do that, right? Now, if you were like an engineering school and you cared more about the math, you might, like, nobody does this because it would be way too confusing, but you could say, like, weight your math twice and your verbal once, right? And so if you scored 800 on math and 500 verbal, then your kind of your reduced dimension thing, but because the math is emphasized, you would multiply the math by 2 and you'd get 1600 plus 500 and you get a 2100 or something like that, right? Whereas if you applied to, I don't know, some other school that said math was less important, but the verbal component, that's really important, okay? They might say weight, I don't know, math 1 and the verbal twice or something, right? And basically what we want to do is we're not going to be the schools that won't care about the math or care about the verbal because we already know what we want. We just want to find, like, how do we differentiate the students the most or something, right? Like, should I weight one more and weight the other less, or weight it negative or something? That's what we're trying to do. But basically, in this example, we're going to take however many dimensions y is, maybe 2 or 3 or whatever, we're going to reduce it down to 1. And the way we're going to do that is we're going to just take some vector w, okay, and multiply it by whatever y is, right? So again, if for example, y sub n could have been like you got 800 math and 500 verbal or something, and W transpose might be like 2, 1 or something. You know, when you do this, when you get this, your x sub n would be 1600 plus 500 equals 2100 or something like that. Okay, we're just looking for whatever this. What do we use for this, right? So this is unrelated. I'll just. Okay, just side note. Okay. I don't know how many dimensions y is, but right now the mean of y actually is centered so that it has a mean of 0. Okay, and so the variance of x, okay, which we'll call sigma squared sub x, is going to be 1 over n, and we're going to take the sum of each xn minus x bar squared, right? So this is just the definition of variance. I guess technically it's 1 over n minus 1, but it doesn't even matter. We'll just do this, okay? And one thing is that x bar is going to be 0 because y bar is equal to 0, right? So we've said we're dealing with a centered matrix y bar. So, you know, if x bar is equal to 1 over n of the sum of x, and we have 1 over n, if each of these things, if x is w transpose y, okay, y sub n for each of these things, this can be w transpose times 1 over n, the sum of y bar n, and this becomes w transpose y bar. So this thing is w transpose 0, a 0 vector. So that's just going to be 0, okay? So x bar is going to be 0 because the mean of y is 0. All right, so so this simplifies, okay, to 1 over n sum of xn squared, okay, because x bar equals 0. All right, so now what we want to do is we want to maximize this thing, okay? We want to maximize this in terms of w. Is that all right? Okay, so we got 1 over n, the sum of x of n squared and want to maximize this. Okay, so this is the variance of x. All right, and so I'm going to have 1 over n. This is going to be the sum of each of my w's, w transpose y bar n squared, okay? And so now, when you square any kinds of vectors, it gets all weird. And so this is going to become w transpose y bar n transpose, I'm sorry, this is not y bar, y sub n transpose w, okay? And I can move some stuff around, and I'll get w transpose 1 over n sum of yn y transpose w, okay? W is technically, I want to do dimensions. Y is 1 by, I'm sorry, this is 1 by m, and this is going to be m by 1. Okay, yeah, 1 by m, m by 1, 1 by m by 1, okay. And I got 1 by m, this is m by 1, 1 by m by 1. Okay, so it's all okay. This right here, this result is an m by m, and this is, what is this? This is technically, so I've got 1 over n sum of y bar n y bar transpose, okay? We can think of this as also y bar n minus y bar, which is 0, right? Times y bar n minus y bar transpose, because y bar equals 0, right? And so this is the variance covariance matrix of y. Is that okay? All right, so now I've got w transpose, and I'm going to just write c w. Okay, so this is the m by m variance covariance matrix of y, and here I've got just my 1 by m weight matrices. Oops, sigma squared x. Okay, and what we still want to do is we still want to find w's to maximize this. So we want to find the w's that's going to maximize this quantity. So how do we maximize this quantity? All right. Well, okay. So the traditional way to find a maximum is, take the derivative and set it equal to 0. Okay. However, when it's just w times a matrix times w, you need to put a constraint on w, right? Otherwise, you're going to just say take w and make it a bajillion, okay? And then the results are really huge, right? So we've got to put a constraint on w. Otherwise, we can just make w infinity and maximize it that way, right? So we must constrain w constrain W to make it reasonable, okay? So so we will just say, so we constrain W, so we're going to just say W transpose W is equal to 1, okay? So we'll just start with that. Okay, so now we have a constrained optimization problem, like, so how do you maximize something subject to a constraint? Do you guys remember? You're gonna hear it and be like, oh yeah. Lagrange multipliers? All right, it's not so bad, all right? The point of the, all right, so, okay. So constrained maximization. Huh? Do you guys remember this? No? Kind of? With,
taking me back
yeah, exactly, right?
all the way to differential equations.
Right, so, okay. So we're going to say L is equal to, this is the thing that we want to maximize, W transpose covariance matrix W, and then we're going to multiply it by lambda times basically this, the constraint, okay, W transpose W minus 1, right? So because this is equal, this thing is technically 0, okay? And so it doesn't hurt to subtract off a 0, right? So we're still trying to maximize this, but we've got this thing in here, right? Because basically we can't let it, this thing has to be true, right? Okay, so anyway, you take the derivative of this with respect to W, all right? So now remember all of our joyous derivatives with respect to vectors, okay? So this is basically C times W squared. So we're going to get basically 2C times W. Okay, and then this is basically a W squared minus 1. And I'm going to, technically, I guess we can have like a 2 lambda W here. And we're going to set this equal to 0. Okay, and then so I get CW is equal to lambda W. Okay, lambda, this is just some scalar. So I've got a matrix C times vector W is equal to scalar lambda times a vector W. Is that right? Are we okay with this? If you don't know the Lagrange multipliers, don't worry about it, all right? I guess this is just to show that, like, what I'm gonna do, like, there's like mathematical reasoning behind it. I guess I could have just jumped straight to the answer and said this is what we do. This is how you do PCA. But okay. Does this look familiar? Matrix times a vector is equal to a scalar times a vector. What's it called? An eigenvector, right? For this to be true, W has to be an eigenvector of the matrix C, right? Okay, so for this relationship to be true, W must be an eigenvector of C. Okay. All right. So maybe you haven't taken linear algebra, or you took it and you forgot this. Okay. It's okay. All right. I'm just telling you that I guess we could have just jumped and said, all right, we want to do PCA, blah, blah, blah. We're going to take the eigenvector of the covariance matrix, okay, after we've centered it. But you can follow this and just say, all right, well, the relationship also works, okay? In that this is going to be the thing that if W is a eigenvector of the covariance matrix of Y, then when you multiply Y times W, the resulting projected values X will have the maximum possible variation, okay? All right, let's just try something silly here. Something's broken. This didn't work. Why is this not closing? Okay. Has been deleted or moved. Yeah. Okay. Well, all right. Let's just try this out here. Okay. So let me find. Maybe this is it. Okay. Computer decided to do stuff. All right. Okay, so here's an example. This is Olympic heptathlon. All right, so heptathlon is, track and field. And so how does this work? Okay, so there's 7 events in the heptathlon, and it's okay. So it's women's heptathlon, and it consists of 100-meter hurdles, high jump, shot put, 200-meter run, long jump, javelin throw, and 800-meter run. Okay, so those are your 7 events, and there's a scoring system, right? So you can like do really awesome on one thing, but do terrible on another, and there's some kind of scoring system, and basically we need a way to rank you, the competitors, from number 1 to last place. Okay, so we need to turn 7 scores, 7 event things, to a single number. Okay, so this is, we need to go from 7 dimensions down to 1 dimension, because ranking is only going to be done on 1 dimension. We can't say, oh, you came in first place in hurdles and 3rd place in high jump, and this person came third place in hurdles and 1st place in high jump, and therefore like you're tied or something like that, right? We can't just do that. Okay, so anyway, track and field, we're going to go from 7 dimensions down to 1 dimension. Okay. Okay, well this is, okay, so I'm going to go ahead and load up the data, and if you take a look at the heptathlon, okay, so we have the 7 scores. Okay, hurdles, high jump, shot put, run, long jump, javelin, 800-meter run. Okay. And then the score is based on the Olympic formula for the score, okay? What we're going to try to do is we're going to try to come up with our own version of the score and see if we can get it to kind of work, okay? We have to kind of we're going to change the directionality of some of these things, okay? So in terms of the hurdles and the 200-meter and 800-meter run, like shorter is better, okay? Lower scores are better, and so to kind of just get everything to kind of point in the same direction, we're going to just reverse them. Okay, so we're going to just do max and this, and we're going to just get rid of the score column. Okay. Oops. Okay, so this is kind of a pairs plot of everything, And if I just kind of look at the kind of the first three columns, okay, we notice there's one competitor who's like far worse than everyone else. Okay, like this is like at the Olympics, generally like everyone's at like top tier type of thing, but you know, for whatever reason, there's kind of one observation that's a bit of an outlier. Okay, so probably what we'll do is we'll get rid of the this is I must not have done something correctly. Okay, so we're going to get rid of the kind of this kind of the worst performing athlete. Okay, and we'll just take a look at heptathlon now. Okay, so we've done this. Okay, let me clean this up here. All right, so I've got heptathlon. All right, and so what I'm going to do is so to just kind of demonstrate how this goes is I'm going to kind of create a vector of means, and this is going to be the column means of heptathlon. Okay, and I'm going to go ahead and I'm going to just subtract off the means from everybody. All right, so that way I think I have to do this, transpose heptathlon minus the means, and then let's transpose this back. I'm going to just call this the centered data. Okay, so here's so the centered data will look like this, and if I ask for the column means of the centered data, we pretty much get 0 for everything. Okay, on the order of 10 to the minus 17 and something like that. Okay, so this is basically I've centered the data, and so now what I will do is I'm going to ask for the variance matrix of the centered data. Okay, and this is my matrix here. Okay, so this is going to be kind of this is matrix C. I will call it this, right? So I can ask, what are the dimensions of matrix C? Okay, and it's 8 by 8. Oh, I'm sorry. I have to get rid of the score. So sorry. I thought I did that already. Okay, I apologize. Let me go back, and we're going to get rid of. So let me just get rid of without the 8th column. Okay, so let me just redo a bunch of the stuff. I'm going to get rid of okay, so there we go. We can center it, and I can take the variance matrix, and we have a 7 by 7 variance matrix, okay? And I can ask for the eigenvectors of matrix C, okay? Do you guys know the difference between the variance matrix and the covariance matrix? I'm sorry, not the covariance, sorry, correlation matrix. correlation matrix versus the variance covariance matrix. So if you take the raw values and you do the variance matrix, you'll get the variance matrix basically, okay? But if you take the raw values and you scale them into z-scores, and then you do the variance matrix, then that's equal to the correlation matrix, okay? So actually, I think what I'm gonna do is I'm going to use the correlation matrix instead. So it's pretty much the same thing as the variance matrix, variance covariance matrix, but I'm going to just kind of scale all of the values so that I don't run into issues where high jump and like the fact that they're measured in different units will throw things off. Okay, so here are my eigenvectors, and I'm going to just take this first eigenvector. Okay, this first eigenvector, I'm going to just take the first one. So I can just do the result eigen $ vectors, and just take the first one, and this I'll call my W. Okay, and then I'm going to do W, or I'm going to take my heptathlon data. Okay, and I'm going to multiply it by, let's see, is this what I want to do?
I think you have to make a heptathlon data matrix.
I have to make it a matrix. All right, you're probably right. Let's see. As dot matrix. Okay, so we're gonna do as dot matrix, and then I'm gonna multiply it by my W. Okay. And so here we go. Okay, so this is kind of the results here. So the resulting scores, all right, and we want to see how closely, like what's the correlation between kind of my scores that I've come up with using dimension reduction via PCA, and so this will be kind of like R scores. I guess we'll call this the PCA scores, and then we can actually look at heptathlon, the original heptathlon scores. Oh dear. I guess I should have called this. Heptathlon 2, where we just only keep the, I hope I did this right. Okay. All right, so let's look at, this is probably not the, all right, so we'll plot our scores, our PCA scores versus the heptathlon. Did I do something wrong? The lengths differ. Did I not? Oh, here we go. Okay, so we have that. I'm going to reload this. What is heptathlon 2? And what is my length of PCA scores? Okay, so now okay, I should be able to do this now. That is not what I wanted to see. Let's see. I wonder if maybe I messed something up here. Let me see. All right. If I do principal components, we can just kind of get this, and This is a bunch of stuff that we don't need. Okay. This is what I wanted, okay? Let me just see what I wrote. So I'd written some code earlier, and okay, so my heptathlon PCA is a result of just running the principal components command, okay? And I can just say, kind of just take the first principal component of what we get, and that plots it down to just one dimension, and we get basically a 99% correlation between our scoring system using principal components analysis and what the Olympics committee determined was the best way to do it. But I must have done something wrong here. Maybe I should have used the covariance matrix instead. I don't know. No, something. Okay. All right. I don't know. This code that I've written, something's wrong. Okay. But so you can do principal components in R. R makes it very easy by just running this prcomp function, principal components, and it will find, you know, kind of 7 principal components. And here's just kind of the weights, the weight matrix of, the weight vector, the weighting vector of the first principal component, which is going to be your most important one. And if we use just our first principal component, we can recover, you know, quite a bit of information as far as ranking the things go. There's a neat little website that shows how this is. So principal components analysis. Okay, so here's kind of a plot where, you know, we have some two-dimensional data, okay, and this green and this red, the red is going to be the first principal component. After you project it down, this is going to maximize the most amount of variation, okay? And then, you know, if I were to move these data points, this updates in real time this thing. And so if I move the data points around this way, you know, it realigns how the principal component should be found, saying that the data should be projected along this red axis. Yes?
So if you're doing PCA or something with just 2 dimensions,
Yeah.
is it the same as projecting through the OLS regression line?
It is not. It is, it's not the OLS regression line. It's the, yeah. So the OLS tries to minimize the vertical distance.
But this is like the distance.
This will minimize the perpendicular distance to the line.
Got it.
Okay. So the OLS, your residual is the vertical distance from the dots to the line. Whereas, yeah, PCA, when you do it, it's minimizing the perpendicular distance to the line, which will be a little bit different. Yeah. Okay. So this is kind of how our data looks in 2 dimensions. In X, it's spread out this way, and Y, it's spread out this way. But then when you project it down to a principal component, it looks like this. And then the second principal component just captures whatever variation is left over, which is very little after you've done this, okay? Here is data in 3 dimensions, okay? So it's kind of neat, okay? And as it rotates, you can kind of see that there's 3 clusters in here, okay? And here, if we just project it down to 2 dimensions, you kind of lose that thing. And if you look only at X and Y and Z, you can't see that there's 3, okay? Now, if I do PCA, what it's going to do is it's going to find the alignment so that it maximizes the variation in the resulting projection, okay? And when we do this, it projects the data. It's find a rotation or projection of the data that maximizes it. And what we see is that even when it's down to looking only at this, we can see that there are 3 clusters in the data. Okay, PC2 and PC3 don't actually contain that much more valuable information for us. Okay, here's a silly example. Not silly, interesting one. Okay, the original data is in 17 dimensions. Okay, and it's on eating habits in the United Kingdom. And so the United Kingdom consists of 4 countries within: England, Northern Ireland, Scotland, and Wales. And then they asked people in England, how many alcoholic beverages do you consume? How many carcase meat I don't know what that is, okay? Cereals, cheese, confectionery, fats and oils, fish, fresh foods, fresh potatoes, fresh vegetables, other meats, other vegetables, processed potatoes, processed vegetables, soft drinks, and sugars. And they say, oh, well, I eat this much and I consume this much, okay? And I say, well, do you see is anybody more different than anyone else? It's hard to see. You do principal components analysis, and it's going to put the 4 points, and we end up with Northern Ireland way over here, whereas Wales, England, and Scotland end up over here, right? And so if you actually kind of project this and take a look, and you look at the different components, one thing that you'll notice is if you look at this row for fresh fruit versus fresh potatoes, okay, in all of the other countries, England, Scotland, and Wales, they eat more fruits than potatoes, okay? Fruits versus potatoes, there's more fruit than potatoes. But in Northern Ireland, they consume a lot more potatoes than fresh fruit, okay? And that's just what we see in the data, okay? And this is enough to kind of differentiate the Northern Ireland. Also, there's a great reduction in kind of alcoholic drinks versus the other countries and stuff as well. Just something kind of interesting as we encounter that. Here's kind of a So here's just a silly thing. Okay, so here's 4 data points. All right. I can subtract off the column means so that everything will have a mean of 0. Okay. And I can take the covariance matrix and call that C. And I can calculate the eigenvectors of this. All right. And I'm going to take my centered y data and just multiply it by kind of my first eigenvector, and that will be my first principal component, okay? And if I do that, then PC1 kind of takes these 4 data points and just projects it down to one value each. So the data exists in 2 dimensions, but I'm projecting it down to 1, okay? I can kind of go back from 1 dimension back to 2 dimensions. So the original data exists in 1 dimension. So I'm going to just take this vector, which exists in 1 dimension, okay, and I'm going to kind of multiply by the transpose of W, and this will kind of give me my reconstructed data, okay? And if I do this, we can see this is how it got reconstructed here, okay? Okay, so this is kind of this line represents the principal component, and what it's doing is it's projecting this dot down to the line. This dot gets projected to this spot on the line. This dot gets projected to this spot on the line, and this dot gets projected to this spot on the line. Okay, so this is where they exist in the first principal component. All right, and let me do this last one. Lots of stuff here. Okay. Okay, so here I have a picture of Audrey Hepburn from Breakfast at Tiffany's. Okay, so classic movie, and this is not practical, but it kind of shows us what dimension reduction can do and how it still kind of what we call preserves the okay, my thing is stuck. I shouldn't have rerun this. Okay, so let me try this. Load down image. Okay, so my picture of Audrey Hepburn is 634 pixels by 791 pixels. Okay, and this is what it looks like. Okay. Now what I can do is I can treat this as a big matrix with 634 dimensions. I can say I've got 791 observations, 791 rows. Each row exists in 634 dimensions. Okay? And what I might want to do is I want to project from 634 dimensions down to something fewer. Okay? And so I'm going to do exactly this. I'm going to find the, I'm going to center the matrix so that the means are 0. I'm going to find the covariance matrix, and then find the eigenvectors of the covariance matrix and use that to kind of identify my principal components, okay? So I'm going to calculate the means, I'm going to center the matrix, and we'll make sure everything's equal to 0, okay? Here's the covariance matrix. The covariance matrix is huge. It's 634 by 634 rows, okay? It's a huge thing. I'm going to go ahead and I'm going to find the eigenvectors of this covariance matrix, okay? And so the eigenvector, there's 634 eigenvectors, but I'm going to just keep the first 50 of them. Okay. And so what I'm going to do is I'm going to project my data down to the 50 principal components, okay? So I have, when I do this, my data is reduced from 791 by 634 down to 791 by 50, okay? So I've significantly reduced the size of my data matrix, okay? 790, it's like, you know, like 1/12 the width, okay? It used to be 634 pixels, now it's only 50 numbers, okay? I shouldn't call them pixels, okay? All right, and so I'm going to take this thing and I'm going to, if I try to plot this, okay, this projected data, it doesn't look like anything, okay? There's nothing, no meaning here, okay? And I should have actually transposed it, okay? Okay, it's just 791 pixels, 50 columns wide, okay? There's no value to this, okay? But I'm going to take this thing, this data here, and I'm going to reconstruct, kind of project it back to 634, okay? So you can imagine if this were some kind of file compression thing, and this is not how file compression works, okay, or image compression works. You could, instead of trying to transport the full 791 by 634, you would compress it down to this. You would send this thing over to your friend, and then you would give instructions to your friend on how to unpack it, okay? And so here I've done that, and when I do that, it's back to 791 by 634, and I can plot this, okay? And I don't know if you can see, so here's what it is. Now after I've reconstructed, let me delete this in between thing, okay? This was the original, okay? And after I've reconstructed it from a thing of only 50 values wide, it's not as high quality, okay? There's definitely some artifacts and image degradation, but we can still recognize this image, and it still maintains kind of the important features and structure within the original data, okay? So what I did earlier was I kind of cycled through, like, what would happen if I kept only one principal component, okay? And then we tried to do this. Okay, it looks like a mess, right? So this is the original thing. And if you look, okay, so if you just think of what the structure is, okay, there's a big white spot here. Her dress is very dark. There's big bright white napkins here. A dark ceiling up here. Her face is fairly light, okay? And this is kind of what we have right now, okay? I'm gonna keep two principal components, and now we're starting to get kind of a little bit more structure here. With three principal components, I don't know why it keeps resizing like that, but with three principal components, it looks like this. So here's 2, 3, 4, 5 principal components, 6 principal components. Now you start to see what could look like a face, okay? And then here's 7, 8, 9, 10, 11, 12, you know, and here's 18 principal components, and now you can tell this is, you know, a woman wearing gloves or something, and something like that, okay? And here we go with, so here's 50 principal components. This is what we had created. Here's 70, 90, 120, and at 150 principal components, it seems, I'm sorry, I don't know why this thing keeps bouncing back and forth. Let me see. I don't know what's going on. How do I, maybe, extra large icons, is that any better? How do I do my icon size? Let's see. Okay, all right. And now at least we stopped resizing here. Okay, so 1, 2, 3, and you can see as I increase the number of principal components to keep the information, I retain more information in the data, okay? And at this point, I'm just kind of increasing contrast in the image, okay? Which, if we think about it, what is contrast in an image?
It's like rapid changes between two adjacent.
Well, it's the variation in the values that you see. The contrast basically says the whites should be whiter and the darks or the blacks should be even darker, right? And so you're maximizing the amount of light variation in the image, okay? And so what we're able to do, as I increase the number of principal components, I'm able to capture more of the very original variation in the full data. So the full data required all 634 kind of columns to have the full variation there, and we're saying, like, how much of that original variation can I capture with just, say, 50 principal components, okay? This is not how image compression works. JPEGs use completely different technology as far as things. I mean, you still have its lossy compression. So if you compress it too low, you get like all sorts of weird JPEG artifacts. But it could be valid as a form of data compression in terms of reducing the number of things. Okay, it's not popular because it's computationally expensive. You have to do a huge matrix multiplication, and you have to undo that matrix multiplication. It's not conducive for something like that. But it is, I don't know, I think it's kind of neat as far as illustrating the idea of taking just any matrix of number, no matter what that matrix represents, and you can represent it into something smaller with only like say 50 columns of data. All right, we'll stop here for now, and I'll check my calendar. Let me see what I've got going on tomorrow morning. I just have to wake up early, right? Let's see. Okay, yeah, I can do. We can do 10 a.m. tomorrow morning for some homework help there. What's that?
No.
Okay, so
Finish homework, yes.
yeah,
Ahead of time.
so we'll do that, and then enjoy your Monday off, or I don't know, Monday of no class, I should say, and we'll see you guys in a few days then.
Are you
Oh,
going
yeah.
to send the